Welcome to NPTEL lecture on a basic course in electric and magnetic circuits. In this lecture, we will discuss more on how to solve different magnetic circuits problems. In the last class, we have discussed on a simple circuit, magnetic circuit, and how to find its analogy that to a DC circuits, and from how to solve the magnetic circuit problem we have seen. Like for an example, we have a magnetic circuit like this with a magnetic core, and we have few number of turns here and a current flowing here I with n number of turns, and this is a core. So, the equivalent circuit for this becomes magnetic circuit equivalent becomes, we have this first, we have to draw the MMF for the magnetic circuit with the proper direction of MMF. So, these are MMF in ampere turn, and then we have the reluctance of the path S, and through which the corresponding flux goes. So, in this case we have different relations, like we talk about N I is the MMF, and for this we talk about S into phi, like we talk about E equals to I into R. So, S analogous to resistance, phi to current, and these to the EMF, E or the voltage. Now, note that in this case the drop across here, the MMF drop across here. So, that we call the ampere turn drop. So, this ampere turn drop becomes equals to S into phi, and for this case that equals to the corresponding MMF supplied equals to N into I. So, from this relation, given the corresponding flux phi and the mu r value for the circuit, line length, the length of the core, and from there we can find out the S value, and once S is obtained and given the phi, we can find out the ampere turn required for the circuit, and in that case number of turns given, then we can find out the I, or if I is given the other way and n is also given, then we can find the corresponding phi for a given value of S. So, with this background we will proceed for few more problems in this lecture. Let us take this example, where I have a magnetic core, circular magnetic core, ring shape, and there is a circuit like this with a uniformly wound coil. Now, what will happen here in this case, that once you have this current injected to this coil and with n number of turns, the MMF is established, and then we have a reluctance path, like we discussed right now. So, for this case also this becomes then MMF N into I in this case, and then we have the corresponding reluctance S here. So, this is a case. Now, what we say here, and the flux phi is there. So, flux phi we relate to this B, and from B we relate to mu into H, the core part, and mu equals to mu naught into mu r. So, given the value of mu r for a magnetic circuit, we can with using the mu naught and mu r, you can find out the corresponding mu, and for the a given value of phi, you can find out the B, and from B equals to phi upon A. From that B you can find out the corresponding H value if the mu r value is given. That is what we have learned. In this example, if you see, calculate the current I which is required in the coil to establish 0.55 milliampere flux in the core. Phi is given here. So, this is flux phi in the core as shown in the figure, given the radius of the mean path r equals to 15 centimeters. So, this is about the radius of the mean path small r shown here. So, up to this why we talk about mean radius, as already discussed in earlier lecture, that from the Ampere's law we know that H L equals to N I, H L equals to N I. So, the length of the based on the length of the magnetic path, the corresponding H will vary. So, across the cross section of this magnetic core, there will be different H at different distances from the center, So, here what we are talking about is the average H, and therefore, we talk about the average R from the center of the ring. Now, the mean given the radius of the mean path r equals to 15 centimeter, a cross sectional area is 5 centimeter square, n is 500 turns. The magnetization curve points of the core are provided in the table below, neglect magnetic leakage. So, there is no leakage in this case. Here the B versus H curve is given, V H curve or magnetization curve V upon H. So, like this, if you plot like this or so, mu r is not given to us. So, we need to mu r to find out the corresponding S also, or so here in this case B versus H given, phi is given and cross sectional area this. So, therefore, B equals to phi upon A, we got the B. So, for a given B, from these values of the B, any intermediate point comes here, and from this intermediate point, so the corresponding H value has to be picked up. So, from that H value, so we know this corresponding operating point V 1 equals to mu into H 1, and that mu we can say that can be obtained there, or the corresponding H 1 can be obtained there. Now, we know the H 1 and the corresponding length. So, H 1 into L is nothing but n into I, and from there you can find the corresponding value of the H L value obtained. So, from there you can find out this mmf value. Once you know the mmf value, mmf upon this n is nothing but your current required in the electric circuit, DC current required in the electric circuit. The other way also we can find out this mu value from that particular point, and for that mu value you can find the corresponding S value, and from the S value L upon mu A, So, that gives us the S value. From the S value also you can find out S into phi, and then from the mmf you can find the corresponding current required for the circuit. So, in conclusion we will see that this is about the corresponding magnetic circuit equivalent. So, we say mmf f equals to n into I, phi the flux in the path, and the S the reluctance, and the ampere turn for this across the S equals to H into L, So, now from this case as given data B equals to phi upon A, that comes out to be 1.1 Weber per meter square. So, this falls out in between these 2 points in between 1 and 1.2. So, midway between this and 2. So, therefore, considering this region as a linear region, we can find out the corresponding H from the table from this one. So, that becomes equals to 850 the initial value plus 1250 minus H 50 upon this 0.2 into the distance required 1.1 from here. So, therefore, that we got the corresponding H value corresponds to 1.1 Weber is 150 ampere turn per meter. So, otherwise someone can plot the B versus H, and from this B H plot you can find out the this plot, you can find out that 1.1 value what is the corresponding H value. So, however, here we have considered a linearity between 1 and 1.2, and based on that we find this to be 150 ampere turn per meter. So, that becomes the H. L equals to 2 pi r, r is given mean radius for this case. So, that becomes equals to 0.942 meter. So, N I equals to H into L, N I equals to H into L. So, that gives us 989.1 ampere turn, and therefore, I becomes equals to ampere turn upon the number of turns 500, that gives the corresponding current to be 1.978 ampere for this case. So, this happens to be 1.978 ampere if it will be applied here, then for this case, for the magnetic circuit like this, the flux will be established will be in the circuit of 0.55 milliweber in the core. So, that is the average flux we can find there. So, this is what a magnetic circuit problem using BH curve. Now, I will go to another example. So, the question here is like this, a magnetic core here and with a coil like this with number of turns equals to n equals to 500 and there is a air gap here in this case, and in this case the question is determine the coil current I for the magnetic circuit shown to establish a flux density B in the air gap. B gap is 0.25 Weber per meter square, Tesla Weber per meter square. Consider fringing. So, fringing is not neglected here, we are considering fringing here. How to accommodate fringing, that we will see. Core thickness 3 centimeter, core thickness 3 centimeter. So, this is what 3 centimeter. So, width of this one is this and depth is 3 centimeter, mu r is 6000 for the core and neglect magnetic leakage. So, whatever flux produced by the coil now goes through the corresponding core and passes through this one. So, when you cause fringing, as you know earlier also, that fringing means the corresponding flux bulges out here. So, that the corresponding area of cross section becomes more. So, note that whatever flux goes from the coil goes here and crosses the air gap, this is phi. But what happens here, because the area becomes more, so therefore, the corresponding flux density which happens to be phi upon A is less at the air gap as compared to the core. So, that is the case in this the effect of the fringing in this case. So, what will happen here, in this case the corresponding magnetic circuit problem, this becomes equals to the MMF plus minus MMF, and then we have the path, the two reluctances, one for the core part and one for the air gap part. This is for the core part and for the gap part, air gap part, and the corresponding flux through is theirs, and this becomes equals to n into I. So, what the question is that to find the I for the given circuit, magnetic circuit, and the equivalent magnetic circuit becomes like this. So, if we can find out the corresponding air gap reluctance and the corresponding core reluctance, then we can find out the equivalent S, and as we know the corresponding, if we know the corresponding phi, then you can multiply with that and you can find the corresponding ampere turn required for this case. So, for this case, as you see here, we will go by one, we will find the corresponding core part reluctance. So, S core becomes equals to the mean length of the iron core. So, that equals to, as per the dimension given here. So, that equals to this part 8 here. So, mean path, we talk about the mean path. So, therefore, 8 minus 2, that becomes equals to 6, this will from here to here it will be 6. So, like that, because of this all the length and breadth becomes similar. So, here also 8. So, this also comes 6 and this will also come 6 and this will also come 6. So, therefore, 4 into 6 and the minus the air gap part, that the core part, core length, and that gives us the 23.5 centimeter mean core length of the flux, required flux. So, area of the core is 2 into 3 centimeter square. So, depth is 3 centimeter. So, this is 6 centimeter square. Mu of the core is mu r into mu naught, and mu r is given 6000. So, that becomes equals to the 7.54 into 10 to the power minus 3. So, therefore, S is L upon mu into A, and this gives us a 5.194 into 10 to the power 4 ampere turn per Weber. So, we find out this S score like that. Next, we will find the S gap, the gap you can say that for this case, for the second part of this one, for the air gap part. In this case, we will again use the L upon mu A, and mu equals to mu naught here, but the A here is happens to be that for the fringing we have to accommodate fringing here, fringing happens to be in the air gap. So, for that the A becomes equals to, earlier it was 2 into 3, in the in the for the fringing to be addressed, it is an empirical formula is that you add the corresponding gap length both to the width and the depth. So, width is 2 centimeter. So, 2 plus 0.5 and 3 plus 0.5. So, the corresponding air gap is added to both the width and depth, and the corresponding area with the corresponding gap becomes 8.75 10 to the minus 4 meter square. So, this is higher than the corresponding area of the core. That is the an empirical way of going by to find the air gap considering the fringing. Note that fringing becomes more and more if the corresponding gap becomes more and more. If the corresponding gap is very small, then we can neglect fringing. That is what we do in most of the problems. So, in this case fringing is to be considered. So, one way of considering the fringing is this way. Now, based on using this corresponding L, mu and A, we find the corresponding reluctance of this gap part to be 4.547 10 to the power 6 ampere turn per Weber. So, the total reluctance of this arrangement for this case become S equals to S gap plus S core, and we added these two and get the corresponding value to be 4.6 into 10 to the power 6 ampere turn per Weber. One observation here, that if you see these corresponding things, so S gap part, air gap part happens to be of the order of 10 to the power 6, 4 into 10 to the power 6, whereas for the core part, if you observe, it happens to be 10 to the power 4 order. So, this implies that the corresponding gap, the ampere turn drop happens to be significantly high as compared to that of the core part, and this is the reason because S for the core part equals to L upon mu naught into mu r into A, and this mu r happens to be large 1000, 2000, 6000 in this case, and that is the reason the corresponding core reluctance becomes much smaller than the air gap reluctance, though air gap length is small in most of the cases also. Now, with more increase in air gap, the reluctance becomes more. So, the MMF required becomes more, therefore, the corresponding current to be injected from the coil becomes also more, and that is not desirable. So, in most of the rotating machines or so applications, we try to minimize the gap. Typically, in a rotating machines 2 mm, 1 mm gap is being maintained in general. So, now for this case the corresponding phi equals to B into A, B is given. So, from that B value we multiply the air gap and the phi to be equals to this. So, this is about the given, because air gap flux is given and we know the air gap area now. So, therefore, from there we find out the corresponding phi. This phi will be maintained throughout the two components, two path, both core and the air gap. So, F, the MMF supplied equals to S, the equivalent S into the phi, this phi. So, that becomes equals to 1006 ampere turn. So, we got the MMF divided by this N 500 here, that gives us the corresponding current to be 2.012 ampere. So, that implies that once you inject 2.0212 ampere, then the corresponding air gap flux will be maintained by the as per the question asked here. So, we see here that for the air gap and the for the air gap with consideration of fringing, how to handle a problem. The next problem is on a circuit like this, a core is given to here. So, we have two sections, one is a thick portion here and one is a thin portion, relatively thinner one. Now, the area of this size is larger and the area of this is smaller, and we say that they have different lengths L 1 and L 2, and L 1 in this case is 10 centimeter, L 2 is 25 centimeter, and the area of the first one is 6 centimeter square and area of the thinner one is 4 centimeter square. The question is the relative permeability of the core of the ring shaped magnetic path is 1000. So, mu r is 1000. the flux density in the thicker section is 1.5 Tesla Weber per meter square. In the thicker one, the flux density B equals to 1.5 T. A coil is wound uniformly across the ring throughout the core. If the current through the coil is not to exceed 1 ampere, it is not allowed to exceed 1 ampere, find the number of turns of the coil. The question is find the number of turns of the coil with a current limiting of 1 ampere. Neglect magnetic leakage and fringing, neglect magnetic leakage and fringing. So, the equivalent circuit for this case will be a coil having a source. So, I put like this plus minus, and these are MMF which equals to N into I, and then we have a core section which happens to be the thick portion, thick, and the S for the thin, and then this give the corresponding flux being established here. So, here also we see here the corresponding flux which is there in the thinner one, same flux also goes to the thicker one. So, we neglect leakage and fringing, nothing is there because no air gap in this case also. Now, in this case the question asks is that the number of turns to be found out for the given limitation of the current for this case. So, the mu r value is given. So, based on the corresponding reluctance, because dimension and mu r value are given. So, S equals to L upon mu a. So, A is available, L available, and mu r is also available. So, you can find out the S for the thicker part and the thinner part, and then equivalent S you can get this plus this, and then this is a series case, flux is same throughout, and then for the given target of flux phi, because area here is available to us, thick part, area available to here also. So, there are the corresponding ampere turn drop here, phi into this and phi into this corresponding ampere turn. So, this ampere turn thin and ampere turn required for the thick. So, these 2 ampere turn. So, the total ampere turn will be available, that ampere turn is nothing but the MMF supplied by the coil. So, using that concept we can solve the problem. So, as mentioned, so the first one, this is a thick section is ampere turn equals to H 1 into L 1, and second thinner section ampere turn 2 equals to H 2 L 2. So, and the MMF is N I and the flux is common to both is phi. So, S 1 into phi is H 1 L 1 and S 2 into phi is also L 2 L 2. So, let us go by this. With this concept, with the given data, we can find out this. So, flux phi in the given circuit is this much, which is common to both. So, same flux goes throughout. Now, thick section, first one thick section. So, we talk about H 1 equals to B 1 upon mu naught mu r. So, this becomes equals to 1194, and so therefore, H 1 L 1 equals to 119.4 ampere turn, and then now for the thin section B 2 equals to phi upon A. You know here, because phi flux is same, but areas are different. So, thinner section has a larger value of B. So, now the corresponding H becomes larger than the H 1, and the H 1 L 1, the corresponding L 1 you multiply, we got the corresponding ampere turn to be 448, and the total MMF required becomes equals to ampere turn for the thin section, ampere turn 1 and the ampere turn 2 for the thinner section, and the combined ampere turn is 567.4 ampere turn. So, therefore, MMF is known to us, and this MMF leads to us this 567.4 ampere turn. So, N becomes equals to 568. Now, with the consideration that our current limiting is 1 ampere. So, if we divide the corresponding by the current 1 ampere, then we got these corresponding things to be 567.4 number of turns. Number of turns being generally considered, not fractional is not considered. So, we make a higher value than the corresponding value. So, that comes out to be 568 ampere turns and 60 number of turns of the coil. So, the answer is that the coil which is wound throughout the core happens to be having 568 number of turns, then with 1 ampere injection we can also meet the corresponding flux requirement of 1.5 Tesla. However, this question can be answered in other way also, as already we have discussed. So, MMF equals to H into L and this equals to S into phi. So, if we find the S 1 and S 2 from the L by mu A formula, so from there we can find out the S 1 for the thinner part, S 2 for the S 1 for the thicker part and S 2 for the thinner part, and from there also you can find out the corresponding equivalent S equals to S 1 plus S 2 and you multiply with the corresponding phi, then also you can find out the required number of turns for the coil. So, this you also can try and find the same conclusion. Now, another example here which is a descriptive example, and from the descriptive example we have to think what is the corresponding circuit looks like and then the corresponding equivalent circuit they are from. A series closed magnetic circuit, it is a closed magnetic circuit comprises of 3 parts. There are 3 parts here, each of uniform cross sectional area, and they are a core length of 8 centimeter cross section 50 mm square, a core length of 6 centimeter cross section 90 mm square, and an air gap of length of 0.5 mm cross section of 90 mm square. So, if you see the air gap that has the same cross section and then the corresponding second core, and therefore, we can consider these 3 in series because they happens to be a closed path. So, the circuit can be like this, that the first part is having a path like this, so it is having a 50 mm square thickness, and then we have a core thicker one like the earlier example you saw, and this thicker one. So, we have a thicker core which is having thicker core. So, this is having a 90 mm square. So, this is having a length of 8 centimeter and this is having a length of 6 centimeter, and the air gap having a 90 mm square. So, we can have an air gap here. So, this air gap having 0.5 mm only. So, this circuit becomes looks like this. So, we have a one core section here and another one a closed section like this, and in between I have the air gap here. So, this is our air gap in this case. So, with this the corresponding data are available to us. A coil of 100 turns are there. So, N we got equals to 100, and then the permeability of the is mu r equals to 1000. Estimate the coil current to produce such a flux density. So, the corresponding equivalent circuit for this case will be if you see, then this becomes equals to the source, that equals to N I equals to MMF, which is wound on part B, that is on the larger size. So, coil will be here. Now, this and with an I and N equals to 100 turns. Now, with this the corresponding circuit becomes 2 circuits. So, we have S 1, we have the gap S g and the corresponding S 2, that is the core S 2. So, or you can say S 1, S 2 and S 3. So, there are 3 parts and each has its own the corresponding reluctances, and the combined reluctances will be S equals to S 1 plus S 2 plus S 3 because flux phi is sent through. So, this is also series circuit case. So, this leads to let us say the section A S A, section B S B and section C S C reluctances. So, combined reluctances becomes S. So, this becomes equals to S A plus S B plus S C, and we know the corresponding flux pi equals to as per the data given B C into A C. So, the that becomes equals to total flux equals to 0.45 10 to the minus 4 Weber as per the data available. So, ampere turn A equals to phi into S A. So, ampere turn here is the drop here, mmf drop here, ampere turn A is phi into S A, phi is available to us. So, S for the A part is L A upon mu into A. So, that we got. So, from that we find out this the ampere turn S phi equals to for the part A equals to 44.1 ampere turn. Similarly, ampere turn for B also S into phi B, that comes out to be 18.4 ampere turn, and ampere turn C we got to be this equals to 198.8 ampere turn. The total mmf required that becomes equals to the summation of the 3 ampere turn, and that equals to comes out to be 261.3 ampere turn. So, now this equals to N I. So, I becomes equals to 2.613 ampere for this case. So, in this example, as I say, you can find out the corresponding reluctances and then find out the corresponding S, and then also you can find out the multiply with phi. So, you can find out the corresponding N I and also do that way. So, ampere turn summation or the corresponding phi into S combination will result in the same conclusion. Now, the next example is on a rectangular iron core is shown. It has a mean length of magnetic path of 100 centimeter, cross sectional area of 2 cross 2 centimeter, relative permeability of 1400 mu r, and an air gap of 5 mm is there, air gap 5 mm here. In the core, the 3 coils carried by the core have number of turns N A. First coil N A is having 600 turns, B is having 200 turns, and C is having 100 turns. And the current associated with them is 15 ampere for this, 5 ampere for the second one, and 8 ampere for the third one. The direction of the currents are shown here, as you see here, one is like this and the other one is like this, and the third one is like this. So, now for this case the question is the direction of the currents taken from the DC source are shown, find the flux in the air gap, find the flux in the air gap, So, for this one we need to first draw the equivalent circuit diagram. So, the equivalent circuit diagram becomes, let us say that depends upon the 3 mmfs required here, the 3 mmfs considered here. So, first one is let the plus minus, if we take this one, the current going in entering and the corresponding flux is in this direction contributed by the first one phi A. So, we say this to be this. So, therefore, mmf here is F A is in this one. Now, there are other, you can say that here if you see this second coil B coil, then the corresponding flux produced by this is in this direction. So, this is phi B produced by this. So, the corresponding flux contributed by this will be in this direction. So, therefore, it means that it is opposing to the first one A, and that is the reason we talk about this mmf to be in opposition minus plus. So, this will be your F B. Similarly, the contribution of the flux which will be there from the C is happens to be right hand thumb rule. So, then this also goes in the opposite directions. So, this contribution of the flux by this will be in opposite directions to the first coil, and therefore, this will be also connected like this as shown here F C. So, these are the 3 sources here, and the path has two, one is core path S core and one is the reluctance of the air gap. So, this becomes your complete equivalent circuit diagram for this one, and the corresponding number of turns N and I for each part is given to us, number of coils. So, we can find out this one, then we can find out the corresponding equivalent F from this one mmf. So, N I mmf is given, and from this core part and the air gap part we can add the corresponding reluctances, and then you can find the corresponding F equals to S into phi, and from there you can find out this phi for the circuit. So, if see here the effective mmf for the circuit becomes equals to, so as I said here phi A, phi B and phi C. So, that becomes equals to NAIA plus minus NBIB minus NCIC, because if you see this voltage here from here to here like voltage equivalent kind of thing. So, this becomes equals to this minus this minus this. So, that becomes NANA minus NBIB minus NCIC. So, we got the substituting the values, we got it to be 7200 ampere turn. So, this F becomes equivalent F becomes 7200 ampere turn. We find the reluctance of the air gap, we find the reluctance of the iron path using the L upon mu A formula for the particular case. Total reluctance S becomes equals to 11.36 10 to the power 6, and then the flux in the air gap becomes mmf by reluctance, mmf by reluctance Ni upon the corresponding S. So, this happens to be equals to 0.634 milliweber in this case. We have another example like a core here. If you see this example, and in this multiple paths, path 1, core section 1, core section 2 and core section 3, and we have an air gap here, and then we have two coils wound here like this, and they are connected in series. If you see the path, 10 ampere current flows here. So, it goes out here, it flows here and it enters here and goes out same 10 ampere here. So, if I go by the equivalent circuit diagram for this, the mmf for the first one, becomes, so this is F 1. So, this F 1 becomes equals to N into I, 10 into 500. So, this becomes equal to 500 ampere turn. Now, we have a reluctance for this path, core part, and then we have a middle part up to B here, and then we have a up to E here like this. So, this part reluctance S from B, A, F and to E. So, up to this point we have a reluctance like this, and then from B to E we have a core, so that is B E core, and then we have a reluctance for the gap. Agree? Now, this part from B C D E we have a reluctance S B C D E, and then we have the source, and note that if this is plus minus. So, flux goes like this. So, from here also if you see the current direction. So, flux goes like this, right hand thumb rule. So, this will be also in the similar direction as the mmf in the first case. So, plus minus like this. So, this is your F 2, and then we close the path like this. So, this F 2 equals to also 5000 here, because both are having number of turns 500 with current of 10 ampere. So, the equivalent circuit becomes like this, and then we need to, from the different value of S and the F, we need to solve the question. The question is determine the air gap flux and the air gap flux density and the field intensity in the air gap. So, for this case the corresponding equivalent circuit diagram becomes like this. So, phi 1 goes from here, and because of the symmetry circuit, phi 1 also goes from here, and the total path, the total flux enters to the central limb in this case, and that becomes equals to phi 1 plus phi 1. This is 2 phi 1 in the central limb, and the F 1 and the F 2 becomes both are 5000 in this case. Now, we will go for the reluctance of the paths. So, this path reluctance and this path reluctance are same from symmetry, and we find this to be both to be 2.58 10 to the power 6 ampere turn. Second, we find the air gap reluctance and the B core part, and then we added this corresponding reluctance path, and we got the corresponding path reluctance path for the B to E section. Now, we consider two loops now. It is first loop and this is the second loop, like electric circuit we do. So, phi 1 into this loop, phi 1 into SBAP from here to here, this part, and then the common path is SB SG, and because there also the phi 1 plus phi 2, phi 1 plus phi 1 2 phi 1, 2 phi 1 into the ampere turn required is 2 phi 1 into this corresponding S of SB part, this part. So, therefore, 2 into this into phi 1. So, this becomes equals to 5000 ampere turn. Similarly, for the second loop, if you go by this second loop, this loop, then for there also the phi 1 for this part into the corresponding reluctance, and here 2 phi 1 goes. So, therefore, 2 into 2 phi 1 into the corresponding reluctance of this middle limb, and that becomes equals to S b plus S g. So, this gives you 5000. So, we got the equation 1 and equation 2. So, we can find from this, you can if we substitute anywhere of the reluctance value, we can find out the corresponding phi 1 value to be like this. This comes out to be 2.067 10 to the minus 4 Weber. So, the air gap flux phi g, as question asks, is 2 phi 1, 2 times of the each flux contributed by the 2 sources. So, that comes out to be 4.134 10 to the minus 4 Weber. Flux density in the air gap is phi upon A g, that becomes 1.03 Tesla, and magnetic field intensity H here equals to B upon mu naught for the gap part. So, that comes out to be 0.822 10 to the 6 ampere turn per meter. So, what we see that for this we can find out the equivalent circuit like this, and that if we solve, then we can find the different flux and the corresponding flux density in different paths also. So, now we will go to the last example. In this example, a ring like this is shown and with an air gap. So, we have seen this kind of example earlier also, but it has two components, part A and part B. So, the question is, the ring type core has a circular cross section with 1.5 centimeter radius and mean length of circumference is 60 centimeter. The ring is wound with a 800 ton coil and has an air gap of 1 mm. So, all values for the reluctance calculation are given to us except the mu r part. Mu r is non known to us. Calculate the current in the coil to establish a flux of 0.8 milliweber in the air gap. So, we need the air gap flux is given, calculate the current required for this, neglect leakage and fringing. The magnetization curve for points for the core are provided in the table. So, the table gives us the magnetization curve. So, earlier also we find in that case also, based on the corresponding B value, we find the corresponding operating point H, and from the H we can find out the corresponding H 1 L 1 plus H 2 L 2, or we can find out the mu r value further. So, from the mu r value we can find out the corresponding total reluctance of the path, and S into phi gives you the corresponding ampere turn required. So, in both the ways you can find out this perspective. So, we have already seen the approach for the part A in answer solution. Like here for the part A, we get the corresponding B value for the gap. So, that becomes equals to 1.13 Weber. So, H c for the core becomes equals to 1100 ampere turn per meter, and ampere turn for the this becomes equals to 606 ampere turn. Ampere turn for the core, we get the corresponding H c from this value of B is 1.13 here, 1.13. So, it is in between these two, it is midpoint between this 1.08 and 1.18. So, we got this to be 1100 this case. So, this is 1100. So, H into L, the ampere turn drop in the core part is obtained, H into L is 660, and ampere turn the gap is H g into L g is 899. The current required becomes 1.95 ampere. So, this we have already seen in the earlier example also. The second part of the question is calculate the flux in the core when 1.2 ampere current flows in the coil. So, this is something different. So, here current is given. So, mmf is given, N into I is 800 into 1.2. So, this is 1.2, this is available to us. So, this is the ampere turn available to us. Here we do not have this mu r value, is not known to us, and to how to find out the mu r value for this case is we need to get into that, because we do not know the B or the corresponding phi or B. So, we do not know the corresponding operating point here, or neither the corresponding H. So, because you do not know the operating point for this case, so we are not able to find the fixed value of this mu r, from which we can find out the H L value or the corresponding S value. For that we need to address like this. In this case, the corresponding N I ampere turn available equals to H G L G plus S C L C core part and the gap part. So, we know the corresponding H G L G equals to the B G upon mu naught into L G plus S C L C, and this equals to you can find out this relates to the corresponding core part. But now we see here in this case the B G in the gap B G equals to B C, this equals to phi, same flux phi divided by the area, and fringing is not there. So, therefore, the corresponding flux density in the gap and flux density in the core same, but note that H is not same in air gap and the core part. So, we can write also these equations to be B c upon mu naught into L g and this equals to S c into L c. So, now we need to find the corresponding operating point. For that the corresponding B h plot is curve is given to us. So, B versus H. So, this plot to be plot. Now, what will happen here? So, this is B for the core and if you see this equation here, we know the ampere turn. So, this is 800 into 1.2. So, this value we know. So, we need to see this operating point. So, here if we see this equation, so this becomes equals to y equal to m x plus c kind of thing for the B versus H. So, B c versus H for the core. So, these are y equals to m x plus c. So, with that concept we will find an operating load line curve and the load line curve will give the intersection point and which will be nothing but this operating point this, and based on that operating point we can find out the corresponding B versus H point. So, in this example in the last discussion we saw about this circuit magnetic circuits and given this corresponding B H data sheet for us. So, from there we say that we can write an equation like that B g L g upon mu naught plus S c L c equals to N I, but you know that B g equals to B c in that core B g the B g the core in the B g and the B c in the core they are same. So, therefore, in place of B g I can write B c and then I got a equation like B c upon 4 pi 10 to the minus 7 into 10 to the minus 3 plus 0.6 S c equals to 960 after substituting the data for the magnetic circuits. So, that gives us an equation like that B c equals to m h c plus c in the form of y equal to m x plus c, where m is the slope of the line. So, if you do that, then we can, this is a straight line. So, this straight line is like this. So, on B c versus H c plot, we have the corresponding core B versus H for the core, that B H curve is from the points we have plotted. These are the points for these points from the B H plot B c versus S c. Now, we are drawing the load line. So, for that the load line, if we use this corresponding equation, this equation. So, there if we substitute S c equals to 0, this point S c equals to 0, this point y axis. So, then we get the corresponding B c to be equals to 1.2 t. So, this is 1.2 t. So, this point and with S c equals to 0. Second point B c equals to 0, this point, then S c becomes in this equation S c becomes equals to 1600 ampere turn per meter. So, this point becomes 1600 ampere turn per meter. So, we got these 2 points, connect these 2 points. So, that becomes our a straight line. Intersection of this point is nothing but the corresponding operating point for this condition or this situation. So, as per the data given here, calculate the flux in the core for 1.2 ampere flowing this, then the corresponding point becomes this. So, the corresponding operating point becomes this. We see about the B c S c for this case. So, the corresponding intersection B c gives us the 0.7 Weber per meter square. This is 0.7 per Weber per meter square, and from there we got this corresponding the flux value B phi equals to B upon A, area is known to us. So, we get the value of the flux to be 0.495 milliweber. So, the question was calculate the flux in the core when 1.2 ampere current flows in the circuit. So, we say that the corresponding current becomes 0.495 milliweber. So, this is a different kind of problem given with the B H curve and the corresponding operating line B versus B c versus S c, that y equal to m x from equation, and then the intersection point gives us the corresponding operating point. From the operating point we can find the corresponding flux value phi. So, in overall in this lecture we solve magnetic circuits problem from simple problems, and then therefrom we can go to the more and more challenging problems also. So, we saw that the equivalent circuit for the magnetic circuit can be similar to that of the DC circuit, and we can have series and series parallel combinations based on the flux passing through the different magnetic circuits, and using the different principles MMF, HL, H into phi u, you can solve the corresponding magnetic circuit problems. Thank you.